Hi friends, welcome to Unit 2, Day 4. This video focuses on function notation, and the graph of a function. This particular video is going to really get in deep into the graphing part for this particular chapter, as we talk about what a function really means. So a function is a relation, we talked about relations earlier, where each element of the domain corresponds to exactly one element of the range. So in this case, for each input, there's only one possible output. These are what you call your real-life examples. If you were talking about the idea of if a company produces X amount of products, then it's going to make a profit of Y. And that profit, Y, is dependent on that X value. So for here, a given graph is the graph of a function. So if it's a graph of a function, if and only if a vertical line intersects the graph in at most one point. So you may have done this previously in other courses where this is called the vertical line test. So decide whether each relation defines a function and give the domain and range for each. So these are relations now. We're going to see if they are in fact functions. This is a line. This is a graph. Will be a graph of a line. I'm going to go ahead and graph it for 1, 2, 3, 4, 5. And then my slope is 2 over 1, so up 2 to the right 1, and repeat that until I run out of graph. This is in fact so this is a line, the domain of it. This is a function because it does pass the vertical line test. And then the domain, these x values, I can have the set of any x's. So I'm going to show set notation. That's the one students commonly are new to seeing this. The set of x's such that x is an element of the real numbers. So that's one way to represent it. Range, of course, is my y value, set of y, such that y is an element of the real numbers. That's also. So this is set notation. So just friendly reminder, this is set notation. Number 2. This one. This is a square root, and to kind of visualize this, let's go ahead and find out what the domain is. Remember, to find the domain of a square root, we set what's underneath the radical greater than or equal to 0 and then solve. So 2x minus 1 is greater than or equal to 0. Add 1 on both sides. 2x is greater than or equal to 1. Divide by 2. So I got x is greater than or equal to 1/2. So my domain, knowing that my domain is included with 1/2. So I'm going to go ahead and use, switch colors here. Let's do interval notation. So I have 1/2, comma, and then that goes for infinity. Now, if I try to put in 0 for this, I'm going to get a negative under the radical. It doesn't work. So it actually doesn't start until 1/2. So at 1/2 of this value, it becomes the y value 0. So I actually know that starting out. And then I know a few other values from doing this previously. 1, 2, 3, 4. It's 2. So we get a graph that looks like this. Now, this is a function. This is a function. It does pass the vertical line test. The range, we can see that it starts at 0 and then continues on. So 0 inclusive, continues on to infinity. 3, x equals the absolute value of y. So this one we got to be really careful with. This is x equals the absolute value of y, not y equals the absolute value of x. So for every value that I'm plugging in this case I'm setting it up where it's x equals, so I'd be plugging in y values. If I set up a t-chart, and I'm plugging in different values of y, and I plug that in, I get the absolute value that gives me essentially the positives for it, which means that no matter what I have for y, I'm going to have a positive value for x, or a non-negative in this case. So what we get is we get something that looks like the absolute value kind of V-shape, but instead of opening it up or down, this one opens to the right. If I had a negative sign in front of it, then it would be opening to the left. This will continue on forever this way. Continue on forever this way. Now, domain, be careful, your domain, it doesn't start, or it doesn't have, from negative infinity to infinity, all real numbers. It can only start at 0. So my domain for this starts at 0. So in this case, we would have, in set notation, the set of x's such that x is greater than or equal to 0. Now, my y values, I can have any value for y that I want. So y would be an element of the real numbers. The other way that I did not show to write, we talked about set notation, interval notation. There's a few others. Those are the two that we really primarily focus on this, because we can also talk about representing it graphically, which we talked about earlier. Those are the two that I'm going to focus on here. Be able to know the difference between the both and being able to communicate and go back and forth between them. Number 4, this is an inequality. Oh, sorry, this is not a function. Not a function. This fails the vertical line test. Any point past 0 fails the vertical line test. It has to. All right, so this one. If you forgot, this is an inequality when we graph inequalities. This is actually a linear inequality. So I can go ahead and set this up right now. It has a negative slope, which means that I'm going to be going down and to the right. And if I connect these with a straight edge, because it's a line, I'm going to use a solid line because it's equal to. If it was just less than or greater than, then I would be using a dashed line. Now, with inequalities, we shade. All my values that make this true are above, so I'm shading above here. And I also kind of shade off the graph a little bit to show that it does continue. A lot of students just think it stops where the grid stops. It doesn't. This continues on forever. In fact, it does continue on forever over there as well, and it continues on above that value. So for this one, this is not a function. And the domain, again, because it's based on, even though it's inequality, because it's based on a linear, kind of a linear setup for the inequality part, the domain is going to be set up on that. So this one would be from negative infinity to infinity. Your range is also from negative infinity to infinity as well. That's an interval notation. For these two on the back, I'm starting to get into a little bit different things. This one is a quadratic, but it shifted 3 units up. 1, 2, 3. So we're shifting here. 1, 2, 3. That's off. So here's this. So is this a function? It is definitely a function. For your domain, you can have any value you want for your domain. Your domain set of x's such that x is an element of the real numbers. Your y values, however, your range is restricted. This is going to be a set of y's such that y is greater than or equal to 3. 6, we get it's a little bit interesting. This particular graph. This is a rational graph. If you think about what we can't divide by 0. So the domain for this particular problem, I can have any number I want. Oh, I'm going to switch over back to my bluish purple. Negative infinity to 2, negative 2, and then union negative 2, non-inclusive, to infinity. So I can't have 2 as a value. I'm just going to show you graphically. We're going to talk about graphing rational functions here soon. I'm going to show you graphically what this particular graph does, because depending on what you had previously in this course, you may be missing out on, kind of what's going on here, x plus 2. So I'm just showing you the graph of it visually. Maybe. There we go. You can kind of see what's going on here is that at this point where it's negative 2, I have kind of this what's called an asymptote. And the asymptote is where it goes and just kind of veers off towards negative infinity here and infinity here. And this graph actually will never touch the value of 0. I can't have the y value be 0. That's because there's a 3 here, and because there's a 3, I can't get 0. Remember, to get 0, it'd be 0 divided by some number. So it actually will never have a value of 0 as well. So for your range, it'll be from negative infinity to 0, non-inclusive, union 0 to infinity. And then, so here I'm just going to sketch this very roughly because we haven't really gone in depth with rational functions yet. So this is like that, and then like that. One thing that you can do is if you're able to graph something and you want to find points, you can use the table, second table, and it gives you some values for that. And I set this up so you can see that negative 2 gives you an error. That's a domain error. So that tells you that actually does not exist on the graph. And this point you can see as a negative, and then this is a positive. So it creates kind of like a mirror effect there. During the next videos, we talk about determining the domain and range of a function with implied domain. Have a great day, friends.